So most welcome to all of you. I thank you for joining us. And please, David, go ahead.
Good morning. Thank you very much for coming. I'm overwhelmed and honoured that so many of you should bother to come and listen to me give some of our ideas that we've evolved in Newcastle. And thank you very much, Bertil and Dick. You're very kind. My background is a general orthopaedic surgeon, trauma surgeon, the old-fashioned everything. In the late 1980s, due to one or two findings, I became interested in the foot, and this became an obsession during the 1990s. And after I retired in 1993, when I found that no one could tell me how the foot worked, it has become an absolute obsession. I've tried to find out how possibly this mechanism that we have at the bottom of our legs actually works. I have come to the conclusion that it is absolutely wonderful, mechanically, aesthetically, and it's the reason that we're here today. It's only been around for about 200,000 years, which in evolutionary terms is just a few minutes. And yet, it's pretty perfect. It's beautiful. It allows us to stand upright so we can balance a big head and a big brain on the top of an upright column. And we can be bipedal. We're the only obligatory bipedal mammal. And we can balance on one leg, on one foot. It is extraordinary. I do not put forward these ideas as being right. I ask that somebody questions them, that you all question them, and that hopefully somebody will repeat or modify, but eventually find out exactly how the human foot works. It was studied in the 1880s by Muybridge in the States. I'm sure you're all familiar with his wonderful pictures. But really, orthopedic surgeons have just said that it's too difficult. Functional control is not understood. No one can tell you how it works. 26 separate bones, impossible to track the talus, and they're not simple hinge joints. And most people have just modelled the foot as a single rigid body. This was one of the things that really spurred me on, is that little is known about the exact biomechanics. Impossible to develop an understanding of the etiology of many foot diseases. So we began by just looking to see what the foot did. And this, believe it or not, is my foot, which has done many years' service. Heel contact. Forefoot contacts laterally, and the toes are flexed down one by one from the lateral side. Weight is transferred to the forefoot, and as the centre of body mass comes in front of the centre of pressure on the ground, the foot starts to alter its posture. And it becomes supinated in the middle, and the ankle moves laterally so that the forces from the ground propel the centre of body mass towards the other foot. If you put indicator sticks on the tibia and on the midfoot, and you get someone to balance on one foot, then there are complicated movements, but yet they are simple. There's the middle of the ankle. And the foot pronates and supinates, and we all know that the tibia internally rotates and externally rotates together. If we put this balancing foot over a pedobarograph, that's an arbitrary neutral position. And you can see that the pressures over the foot are fairly equally distributed, and the center of pressure is in the middle. And I've aligned it with the center of the ankle. Now, relating the tibial and foot rotations to the center of pressure. This is neutral. If the foot, midfoot, supinates, you see that the ankle moves laterally and the tibia externally rotates. There's neutral again. Come back into pronation of the midfoot, and the ankle moves medially. And we've all got this mechanism. The problem is, how do these complicated movements occur, and what controls them? And somehow or other, despite these movements, the foot remains stable in all these positions, and in between these three positions that are shown. If we look at from the lateral side, then you can see that tibialis anterior is contracting every now and again to stop you falling backwards. If we look at the pedobarograph, as we move from a pronated position to a supinated position, you can see this pattern emerge. Center of pressure moves laterally. And we can arbitrarily divide it into three positions. Pronation on the left, neutral in the middle, supination on the right. That's the midfoot rotations. Pronation, the arch, if you want, I don't like the term, is flattened. And supination, the arch is elevated. And if you look at the position of the center of pressure, you find that not only does it move from medial to lateral, but it moves from anterior to posterior. So this movement of the foot on the ground enables the center of pressure to be moved medially and laterally and front and back. It's not much, but it's such a sophisticated mechanism that it can balance us with this slight movement correction. The medial side of the foot when weight bearing is obviously longer than the outer side. The lateral side, the weight bearing area, is shorter. Now, one of the things that I'm suggesting is that the foot is a balanced cantilever, in that the movements that we have in the foot enable 3 points to stay in line in a sagittal plane, and so the foot is, as it were, balanced. In the neutral position, if you draw a line from where we would imagine the tendo Achilles is attached posteriorly, bring it through the center of pressure and see where it crosses the forefoot, it's between the second and third metatarsal heads. In a neutral position, I suggest that's the balance line, or can be regarded as such. If we do it in the pronated position, the back of the os calcis where the tendon Achilles is attached, center of pressure, then you find that the line moves medially towards the space between the first and second. And then, of course, in the supinated position, so I suggest that the foot has the ability to be put in a whole series all the way through from full pronation to full supination, where these 3 points are in line, and the foot can therefore be a balanced cantilever in all these positions. So that's the query. That's what I think it is. And I'll try and produce evidence as we go along to support this. Now, just quickly reviewing some of the previous concepts, because we've adapted some of them, perhaps illegally, but I think hopefully, helpfully. The foot has been said to resemble a twisted plate, but it's been presented as a continuous twist from back to front. This was accompanied by the idea of a closed-packed and loose-packed position when the midfoot was supinated and pronated. So Basmajian and McConnell said that it was a close-packed when the midfoot was pronated, and the joints were all close-packed and it was firm, and then when you became supinated, the joints were a bit loose and the foot was mobile. The stability of the foot was also suggested that it should be by the axes of the talar-calcaneal navicular and the calcaneocuboid joints, whether they were in line or out of line. And this was, of course, by Elftman. But the stability position was exactly the opposite to Basmajian and McConnell. They thought, at least Elftman thought, that the stable position was when the axes were out of kilter, in other words, in the supinated position. There's been the idea that the foot had arches and that there was medial and lateral columns. And this has held sway for many, many years. And then there was this lovely idea from Dodonka and Kowalski that there was a central stable segment, second and third metatarsals, including the middle and lateral cuneiforms. And they thought that this was supported medially by the first ray, laterally by the fourth and fifth, rather like a child's tricycle, when he was trying to learn to ride a bicycle, the little outriggers that you attach to the back wheel. Many have calculated axes of movement in various parts of the foot. So there's these been the main concepts that have been put forwards. But none have been able to give accurate descriptive details of how and why the tarsal joints move and how they are coordinated. And no explanation, apart from the close-packed and loose-packed, has been given for the structural stability of the foot as its posture alters. And it does alter all the time. So over the years we've done a literature search, and we've gradually adopted and altered previous concepts. We looked very carefully at the wonderful work of John Hicks, some of which has not been read properly and some of which has been ignored. And then the works of Professor Lewis on comparative anatomy and Hewson, they helped me enormously and transformed my ideas. And then we carried out a few studies in Newcastle, which I managed to get free of charge. As a result of this, we've modified the previous concepts. It has become apparent that the foot doesn't have a continuous twist from back to front. It twists in the middle and untwists at the back and the front. So if the middle of the foot supinates, you have pronation movements at the back and the front, so that the forefoot stays horizontal, the talus dome stays horizontal, so that the tibia can remain roughly upright. I hope to convince you that Dodonka and Kowalski's second and third metatarsal raise is a wonderful idea, but it can be extended to include the navicular and the cuboid, and that this gives us a central, stable forefoot segment. As far as the medial and lateral columns, we would ask you to discard any idea that the foot has arches. Arches need foundations. You'd have to dig a foundation to put the foot in every time you moved. But what we have done is suggest that these two medial and lateral columns don't have to be thrown out completely, but they are, as it were, additions to a central beam down the middle of the foot, and that sometimes the central beam is aided by the first ray, sometimes by the lateral fourth and fifth rays, and of course, at times, by the whole of the forefoot. My main aim is to convince you that there is a central longitudinal foot beam, a beam down the center of the foot, talus, calcaneus, and the central forefoot segment. Now, how do these fit together? Well, if we go back to John Hicks and his papers in the 1950s, he had this wonderful description of the great toe extension test. And from this, the drawings, his original diagrams are there on the left-hand side, and you're all familiar with them. And he described the windlass mechanism and also the reversed windlass mechanism. Now, the windlass mechanism, dorsiflexion of the toe and tightening, shortening, apparent shortening of the plantar aponeurosis, resulted in what he described as elevation of the arch. But his reversed windlass mechanism, which he also described in great detail, where if the foot becomes weight-bearing, the ends of the feet move away from each other as the foot flattens, the aponeurosis again tightens, and the toes plantarflex. This is unique to the human foot. Hicks also had the idea that the aponeurosis really resembled a tie bar, and that the foot was a bowstring beam structure, a mechanism and structure used in the construction of bridges. And this gives me the opportunity to talk about one of my favourite bridges, the high-level bridge in Newcastle. It was built by Robert Stevenson in the 1849, completed, and is part of the railway system which he and his father developed. This wonderful bridge has 5 bowstring beam structures, which you see there, stuck on the top of stone pillars. It has not required major renovation for 150 years. It was the first major example of a wrought iron so-called tied arch or bowstring girder bridge. Curved beams are braced by a longitudinal bar tying the ends of the curve together. A railway platform was put on the top, pedestrians and a roadway there, and it's still like that. And if you take out the added things, there is your bowstring beam structure with a strong, stable tie bar. No foundations are required. You can just lift it up and stick it down somewhere. There it is, resting on its stone pillars. The human foot is an adjustable bowstring beam structure, supported by plantar ligaments and adjusted by the windlass mechanisms of the plantar aponeurosis. The windlass mechanism, where the toes go into dorsiflexion and the beam arches, and then the reversed windlass mechanism. Now, as a result of looking very carefully and deciding that it was, in fact, it is a bowstring beam structure, and that we have a central forefoot segment, I am suggesting to you that the foot can be regarded as a 4-part structure. So this is the outline of what I'm hoping to convince you. It consists of the toes and the plantar aponeurosis, a central forefoot segment of the second and third rays, and the calcaneus and the talus, and they form a longitudinal beam. This is supported by 3 layers of ligaments, the capsular and deep plantar ligaments, the long plantar ligament, and this most important and unique thing that we have, the plantar aponeurosis. The plantar aponeurosis forms a tie bar system linked to the toes and the windlass mechanisms. And all these support the longitudinal central bowstring beam. Now that's fine. That's supporting a longitudinal structure. And then I happened to read Professor Lewis's book, which was published in 1989, where he reviewed comparative anatomy of hands and feet. It's still available. You can find it in Amazon second-hand copies. It's wonderful. And he produced this idea that, in fact, we have a propulsive mechanism that's in 2 parts. Whereas most animals, the dinosaurs and the birds, and all mammals except us, have a continuous structure, the superficial digital flexor or plantaris, that goes from the back of the humerus all the way to the toes. We have done away with plantaris, but kept its tendon as the plantar aponeurosis attached to the calcaneum and the plantar plates. So this is our propulsive mechanism, powered by gastrocnemius and the quadriceps, and an energy-efficient plantar aponeurosis which controls the toes. It allows our foot to be plantigrade and digitigrade. We can have our heel down to the ground, or have it off the ground as the cat and the dog and the horse and all the rest of it. But then there was this sentence: lateral swing movements occur at the transverse tarsal joint. This is a unique feature of the human foot. And this stopped me in my tracks, because everyone talked about arch rising and falling. And here was someone who said, actually, the thing that's different about the human foot is that it moves from side to side. And when one put his original drawings so that they fitted on top of each other, rather than being side to side, this lateral swing movement that he described at the transverse tarsal joint became pretty obvious. And we've confirmed this on investigation. So this four-part structure has the ability to move medially and laterally in the middle. It's supported by 3 layers of ligaments. There's a tie bar system which controls it without muscle activity. We have a longitudinal structure which is capable of rising and falling, but also twisting in the middle and moving from side to side in the middle of the foot, at the mid-tarsal joint. There's this lateral swing movement described by Lewis. And I would suggest to you that these movements enable a lateral balance mechanism which are controlled by tibialis posterior and the peronei. When one contracts tibialis posterior, its deep part goes round the medial side of the head of the talus, so it pushes the middle of the foot laterally, and the midfoot supinates. And then when the peronei contract, exactly the opposite happens. And it's rather like the mechanism that a juggler uses to balance a vertical pole. So I need to provide you with some evidence for these strange ideas. And an explanation is also required as to how the foot manages to remain stable as its foot structure alters its posture, often very rapidly. So these are the 4 important and unique mechanisms that I must try and explain to you. The multisegmental tie bar support system with the plantar aponeurosis, a plantar pad mechanism that we've found with the help of MRI scanning, convince you that there's a stable central forefoot segment, and then that these lateral swing movements at the transverse tarsal joint do in fact occur, and how they are coordinated to enable the foot to function as a balance lever. So, the plantar aponeurosis. I'm suggesting that it joins up with the transverse forefoot tie bar consisting of the plantar plates of the metatarsophalangeal joints and the intervening deep transverse metatarsal ligaments. That when you're standing, the reversed windlass mechanism brings the toes down, and we have a basic structure of bowstring beam mechanism. That the forefoot spreads, splays, and the transverse tie bar tightens. plantar pad mechanism. The plantar pad lies between two layers of the plantar aponeurosis and acts like an airbag or pressure bag beneath the forefoot. The stable central forefoot segment, and it forms a four-part central beam structure, and then this lateral swing movement. And the basis of all this is that these movements enable the center of pressure underneath the forefoot, the line of force, the weight-bearing force through the dome of the talus, and the support structure at the back, either the tendon of Achilles or pressure under the heel when you're standing flat foot, can remain in line and the foot act as a balanced cantilever. Now, all I ask you is that you remember that in movements around the longitudinal axis, I prefer the terms supination and pronation and not inversion and eversion. There's a colour code in that I use green for supination and pronation is pink. That was easy. Pronation and pink both have P's. I couldn't find an obvious colour that began with S, but there is green pea soup. So if you remember that green is green pea soup, and that's supination. So the multisegmental tie bar system, it prevents the plantar aponeurosis, prevents the ends of the curved structure moving apart when load bearing. And you may understand, I think, just how unique it is in the human foot if we just look at how it has evolved. When our early ancestors crawled out of the sea, their fins were used as paddles, and they would row themselves over the ground. And then as limbs grew stronger, the body was lifted off the ground. And they didn't become such long creatures so that they didn't sag in the middle. Muscles on the dorsal aspect of the limbs became the epaxial muscles, protractors, which lifted the legs forwards. And the ventral muscles were hypaxial, and they kept the limbs against the ground, and they provided the propulsive power. Some muscles crossed more than one joint. In the early amphibians, there was only one posterior calf muscle mass, and it went into a single tendon, which we will call the plantar aponeurosis, and that went on into all the phalanges of the digits. And if you look at the frog, which has survived for 400 million years, it's quite extraordinary this amphibian has lived so long. It has its toes flat on the ground. And you'd think, because it makes such slow progress when on land, it would have been gobbled up by now by its predators. But of course it has this wonderful business of being able to jump and frighten any predator. Its posterior calf muscles and its plantar aponeurosis form a continuous structure from the back of the lower femur. That's important. It goes round the back of the heel, ankle, and then into the toes. When the hip and the knee extend, one can get this jump. Everything contracts together. But it isn't just muscle. There's another mechanism as well that enables the frog to jump so excellently. Its posterior calf muscle, being attached to the lower femur, gets dragged upwards away from the ankle as the knee extends. And when it's fully extended, the calf muscle origin has been pulled proximally, and of course it contracts as well. So it's a double system. And this is present. It's present in the dinosaurs. It's present in most mammals. And it's certainly present to a certain extent in us, the gastrocnemius. I've called it a sling-spring mechanism because there's a sort of sling around the back of the ankle which contracts, as it were, and pushes the leg forwards. I think it's the earliest sling-spring mechanism in the frog that there has been in evolutionary terms. There's its gastrocnemius, and it will get pulled proximally as the knee extends. There we are. And it can jump an enormous distance for its size. It's quite extraordinary. So there was early end stages, there was just the one primordial muscle at the back of the calf, inserted into all the phalanges. But in the reptiles, this developed into 4 layers. Gastrocnemius, the superficial digital flexor, which both came from the lower femur, superficial digital flexor we can call plantaris, and then middle flexor and a deep flexor. And that was the pattern. The deepest ones were inserted most distally. And the superficial tendons divided when they came near their insertion to let the deeper ones through. And you can see this in your hand, in your toes. It's still there, a basic pattern which has been there since the day the reptiles developed. And of course gastrocnemius was inserted into the heel region. The superficial digital flexor or plantaris in these animals was inserted into the base of the proximal phalanx. But those two, the gastrocnemius and plantaris, came from the lower femur. The initial animals were sprawlers, reptiles. And then the dinosaurs came along, and they did this by rotating the legs. The legs became rotated forwards, and the upper limbs were rotated backwards. And then the knees were extended. And as they did that, of course, the origin of the gastrocnemius and the superficial digital flexor or plantaris were moved away from the ankle. And so the muscular structure just lifted the ankle off the ground as the knee extended. And you can still see this. Have a look at your dog. Bend his knee right up, and you can then dorsiflex the ankle. And he can sit with his ankles on the ground as well as his paw. But as soon as he stands up and the knee extends, his ankle, his heel, comes off the ground. So that was the basic pattern that went into the dinosaurs, and it was also present in the mammals. The interesting thing is that the only animals that managed to be bipedal were those that kept the superficial digital flexor attached to the proximal phalanx, so that the toes were flat on the ground, just as ours are. Birds have their toes all flat on the ground. The dinosaurs certainly did, and the hopping marsupials do. It's this straightening of the knee that's the reason why most animals with vertical limbs have their heels off the ground. They're digitigrade. The dinosaurs. They were very successful, millions of years. Then the mammals came along. And as Lewis comments, they had something different from the dinosaurs. They had a twisted tendo Achilles. So gastrocnemius came from the back of the femur, and as it came down the calf, it twisted to be inserted or pass over the calcaneus and then onto the toes. And as it twisted, Plantaris also came out on top of it. Plantaris went over the heel, gastrocnemius was inserted into the calcaneus. It's present in all mammals, different from dinosaurs. But the early mammals did something different. Their plantaris, superficial digital flexor, was inserted into the middle phalanx, not the proximal one. And so they developed the claw foot. Only the metatarsal heads and the phalanges were in contact with the ground, not the heel, when they were walking. And it was still the same mechanism of straightening of the knee and plantar flexion of the ankle, the sling-spring mechanism from gastrocnemius and plantaris that produced the power, with the calf muscle being pulled upwards. Classic example, of course, of this is the kangaroo. And what happens is his feet are in front of him. Centre of body mass then comes forwards as his legs coil up. And then once the centre of body mass is in front, he can straighten his legs and propel himself forwards. And this is shown so beautifully here. There. Now everything curls up, flexes down. And once the centre of body mass is in front, away we go. And the main power is coming from the quadriceps. Hip extends, but the quadriceps really extend the knee, and that pulls the posterior calf muscles proximally. So there's the early mammals with their pawed feet. That's plantaris, superficial digital flexor going to the middle phalanx. We had all the cat and dog families. There was a further adaptation of the superficial digital flexor in the camels, because this time the superficial digital flexor was inserted into the head of the proximal phalanx as well as the base of the middle, and this allowed the proximal phalanx to be elevated, but the middle and distal phalanges stayed on the ground and a pad formed underneath. And then the ungulates, all the hoofed creatures. The superficial digital flexor went down to the distal phalanx. And so the only thing that was in contact with the ground was the tip of the distal phalanx, and the nail became developed as a hoof. because they haven't any claws, they can't kill things. They're all herbivores. And then we came to the primates, who went up into the trees. And they developed grasping hands and feet, and their nails developed instead of claws. The first metatarsal and the first metacarpal became abducted, and the lateral two rays became supinated so that they could grasp branches. Now the problem for them was the fact that if they kept superficial digital flexor going down to the digits, then every time they moved their knees, it affected the grip. Their digits would be altered, the posture. Now this is what I suggest has happened. Because those early primates, they moved the attachment of the superficial digital flexor to the middle of the foot, away from the digits. So they could still spring, they could still jump. The lemurs are great jumpers, and they could still grip. And they had a good grasp. And in the Galago, they actually lengthened the navicular and the calcaneus so that the lever was strong and longer. And then we come to our nearest relatives, the gorillas and the chimpanzees. And their superficial digital flexor just wasted away, as ours has. And in them, the plantar aponeurosis just became degenerate fibres in the sole of the foot. They had a strong grasp, but when they walk, the middle of the foot breaks, and they don't have a curved beam structure. But in man, although the plantaris disappeared, the plantar aponeurosis, the tendon of the superficial digital flexor, became attached to the calcaneus and the proximal phalanges, and we have the plantar aponeurosis. And this, I suggest and believe, is the change in the foot musculature and construction that is responsible for us being here today. Gastrocnemius is retained. The foot could be plantigrade or digitigrade. When we weight bear, the plantar aponeurosis tightens and the toes come down. They act as a platform, and we can jump, walk, run. It's unique, a two-part sling-spring mechanism. Muybridge documented this sling-spring mechanism in man so beautifully in 1889. And you can see it today on the Olympic screens. They're crouching, everything goes down and flexes, and then sling-spring, and away we go. I'm just trying to suggest to you that actually this plantar aponeurosis is important because most of the textbooks ignore it. The reversed windlass mechanism is hardly mentioned. And this is the basis, really, of how our toes work, and our toes are important.